Hello everyone, I am Shubham Garg, and today in this course we are going to learn about a tool that is CircuitVerse. Okay, in this tool we are going to simulate various logic designs and we are going to see how the logic designs are functioning via this tool. Okay, so here on my screen you are seeing the dashboard of the CircuitVerse and you can see there are designs that I have already made, that is ALU, subtractor, logic gates, using mux, logic gates, normal, multiplexer, half adder, and so on. Okay, so this is the dashboard of CircuitVerse. So first of all, let me take you all to the home page of CircuitVerse. So what you need to do is you need to write CircuitVerse, okay, and then you need to open the screen for the CircuitVerse. All right, so first of all, you will open this website, that is circuitverse.org, and here you will land onto the home page of CircuitVerse. All right, so in the home page what you need to do is you need to sign in. You can see here I am already signed in, so I am not signing out again. There will be a sign in option here and you need to create an account first using your Google account, then verify your Gmail, and then you can sign in using your Google account. All right, so once you create your account and password, you can sign in, and once you sign in you will see a dashboard like this. All right, so here you will see all your circuits if you have made any circuit. Okay, and this is how you are going to see the dashboard. All right, so now what we need to do is, first of all, we need to create a new simulation. All right, so what we need to do is we need to click on this simulator, so it will open this screen, that is circuitverse.org/simulator. All right, so here you will see various options to create the circuits. Okay, so first of all, let us go through all the options which are available. This one is the project name, so it is untitled, so let's save the name as let's say logic gates. Okay, and this is the circuit name. You see, in any project there can be n number of circuits, that is, this circuit name is main. So for example, what I can do is I can write this name as AND, that is for AND gate. So you can see on top here there is this AND gate. Okay, now what I can do is I can click on plus and you will see it is asking for the another circuit name, and I can write OR. You can see here in the same project logic gate we have now two circuits, that is, one is and one is OR. Okay, so these two circuits we can create AND gate in the AND circuit and OR gate in the OR circuit. And one more benefit of doing this is, let's say if we need to make another circuit, something we need to make it using AND OR gates. Okay, so what we can do is we can create a symbol, we can use the subcircuit of AND gate and subcircuit of OR gate directly in this AND OR gate, in this AND OR circuit. Okay, we will see how we can do that later. Okay, so I will just delete this AND OR and I will delete this OR as well. Okay, so now next thing is these circuit elements, that is input, output, gates, etc. Okay, so there you can see inputs. This is the digital input. You can see any input or any element. When you hover your mouse, you will see on bottom right there is the tip for the tool. That is what this element is going to do. So this is the input tool that will toggle the individual bits by clicking on them. Okay, so let's say you need to pass 1 or 0 in any circuit, you can use this input. All right, similarly this is power, this is ground, this is a constant value. It depends on your need. Next thing is output elements. Okay, so here you can see again output tooltip. So basically this element shows the output in binary. Next you have LEDs, 8 segment display and everything else, so that you can display the output according to your needs. Okay, next thing is the gates. All the basic gates are available here, that is, this is AND gate, OR gate, NOT gate, XOR gate, XNOR gate, NAND gate, NOR gate, everything is available here. Next is decoders and multiplexers. So you can see here, this is a multiplexer, this is a demultiplexer, and all these circuits are available in this decoder and plexers elements. Okay, next you have the sequential elements. Here you have your flip-flops and latches. Okay, basically flip-flops only, because latches comes under combination, but here you have a D latch. Okay, so these elements you have here. Next is annotation. Okay, let's say you have to write anything in your circuit. For example, let's say you create a circuit somewhere, and now you need to write here. Okay, not the rectangle, this text one. Let's say you need to write here that this is AND gate. So you need to just put the text here, and in this text column you need to write this AND, that is for AND gate. So that you can label anything on circuit, and this is for image. Let's say you need to attach an image, you can use this image annotation. Okay, and by double clicking you can attach any image. So I am going to delete it for now, and these are the miscellaneous elements. Okay, these are the flags for debugging and plotting, and all the other miscellaneous elements. That is, see, an adder is there, the whole arithmetic and logical unit is there as well. All right, so these are the circuit elements. Now next thing, this is the timing diagram option. Whenever you create a circuit and when you simulate the circuit, it is going to create a timing diagram using the timing diagram option. Okay, which I am going to show you. So from that we can plot the timing diagram. All right, you can see here this flag option. When I attach it to the input or something, so there it is going to plot. You can see here F1 is coming here. There is no signal, that's why no diagram is coming, but this is how you are going to attach. Okay, for now I am going to delete it because it needs to be inside the wire like this, and there should be the input. Let me just attach an input and show you. Now you can see here the timing diagram is moving there. The moment I make it 1 or 0, it is shown in the timing diagram. All right, so these are the basic elements, and this is the timing diagram option. Okay, apart from that, there are several other options like export as a file, save online, and everything. So these are the options, and in this tool we are going to make various circuits. We are going to start with the logic gates, and we are going to then use the logic gates as sub-circuit to create some other circuits, and then we are going to move towards some higher order circuits. Okay, so this course is basically for those who are beginners in the field of VLSI or digital electronics and want to understand the working of the basic digital circuits. Okay, so I am going to start from very basic, that is from the logic gates, and I am going to move towards some complex circuits. All right, so now first of all I will just delete everything. Okay, so now I am going to just attach everything from the beginning. So here these are the gates. So first of all I am going to create an AND gate. So you can see I just need to click here on the AND gate, and I just need to move my mouse here, no need to drag, and just click here. So I have created this, and now the moment you hover your mouse on this end, you will see this circle. That is, just double click on it and increase the wire as much as you want. Similarly you can do it here, and now these are the inputs. So I need to specify the input. So here I am going to specify the input as here one input, and here is another input. Now this thing is for the output. So here I am going to select the output, and I am going to measure the output in this. Okay, so this I am going to measure the output. Now from miscellaneous, to plot the timing diagram, I am going to select this flag option. So now remember the flag this probe, that is the green dot of the flag, should be connected to the wire. All right. So now I'm going to just place it here. Okay, similarly, I'm going to place the other flag over there. All right, you can move the probe by using the arrow keys, or you can select the orientation from here. All right, so I'm going to select the orientation up for this so that I can just place it here. Okay, so I have placed the flag in both. Now you can see there are two waves, that is F1 and F2. All right, now I'm going to create another flag and I'm going to place it in the output. So here, this is the flag 3 and this I have placed in the output. So now I'm going to give some values. It is 1 1 and the output is 1. So now I am going to just change some values and then we are going to verify our circuit using the timing diagram. All right. So now you can see there are changes in the values. Now I have paused the timing diagram. Now let's look at the timing diagram in a bit detail. All right. So now you can see here in F1 column. Let's start from here. Let's start from this point. Okay. Yeah. So this F1 is 0 till here, F2 is 1. Okay, and in AND gate 0 1 is 0. So the output is 0 till here. Next F2 is 0 till here, and the output F1 is 0 and then 1. So if any of the one input is 0, the output is 0. Now from here at this 883 time, around almost 883 time, both the inputs are 1. Hence the output is 1 till the time both inputs are 1. Okay, similar, and the moment one input becomes 0, the output becomes 0. So this is how an AND gate works. Okay, I hope you have a basic understanding of the AND gate and you know how a truth table of AND gate works. Okay, for this gate only I am going to write the truth table, and then in future I am not going to write the truth tables for the logic gates. Okay, so this is 0 0 1 1 and these are the other inputs 0 1 0 1. All right, and now the output is for 0 0 it is 0, for 0 1 it is 0, for 1 0 it is 0, and for 1 1 it is 1. Okay, so this is the truth table for AND gate, and now we have successfully created the AND gate. Similarly, next we need to move towards the OR gate. Okay, so here I am going to write the circuit name OR. Okay, so here this is the gate. So from here I am going to take the OR gate and place it here. Again I am going to take the input and I am going to place it here. And there is the second input. This I am going to place it here. Now comes the output. Output will be on this side. Now we need to put the flags. That is this flag. Okay, so this is the F1 and this is F2 and this is F3 for the OR gate. All right, so now you can see I am going to change the values of OR gate again and we will observe the output. You can see here also that when both the inputs are 0, the output is 0. When any of the one input is 1, the output is 1. Okay, when both the inputs are 1, the output is again 1. That is how an OR gate functions. All right, so you can see in the timing diagram as well. Okay, so F1 is 0, F2 is 0, so F3 is 0. But since F1 is 0 here and F2 is 1, the output is F3 is 1. All right, similarly when both are 1 also, the output is again 1. So this is how the OR gate functions. Similarly, you can use all the other logic, all the other gates and can make the circuit of all the gates as well. So this is like an assignment for everyone watching this course to develop the circuits of the logic gates. All right. So I'm going to put it into the assignment column, and what we need to do is create the circuit. Okay, in the CircuitVerse, and then add the screenshot. Okay, that is, this is the circuit screen with the timing diagram. what you need to do is just take a screenshot and attach it in the assignment column. All right. So this uh, making the circuits of all the remaining logic gates will be your assignment. That is NOT gate, NOR gate, NAND, XOR, and XNOR. Also, you can make AND and OR for your practice as well. So I will just name all the gates in the assignment, so there will be no confusion. Okay, so after the logic gates, let's move ahead and let's move towards the decoders and plexers. All right. So now what I'm going to do is I'm not going to create any other project. I will just create a new circuit here, and I'm going to write here mux. All right. So now here I'm going to take this mux and I will put it here. Now I'm going to specify the inputs. There is the input 2. Okay, so now this is the input for the select line here, and finally this is the output. So now first let us discuss the working of a mux. All right, so you can see what happens in a mux is there are two inputs, that is A and B, and there is a select line, that is S, and there is an output, that is O. All right, so basically A and B, these are the okay, so basically these need not to be in the inputs. Basically there is a select line and there is the output. These two options are A and B. So now what happens, this is a 2:1 mux. All right, that is there are two values and only one value will reach to the output. Okay, so now S can be either 1 or S can be 0. So when S can be 1, the output will be B. Okay, and when S is 0, the output will be A. All right, so I will just label A and B for you. This is A and the below one is B. All right, so I hope it is clear. The above one is A and the below one is B. Yeah, I think it's more clear now. And this one, this is S, that is the select line. All right, so now you can see here when S is 1, all right, the output is B, that is the value of B. When S is 0, the output is A. Let's say I make A 1. So when S is 0, again the output is A. That is 1 is traveling to the output, the value in A. Similarly, when S is 1, the output is B. That is since B is 1. So you can see when I make the B 0, the output changes because S is 1. But when I change A, there is no change because the select line is 1 and it is selecting B to reach the output. All right. So this is how 2:1 mux works. All right. So now what we can do, one thing is, let's say this is a 2:1 mux. Okay. Let's say we need to make a 4:2 mux. So what we can do, we can increase a bit width from here. All right, just a second. Yeah, we have already made the connections, so that's why it is showing like this. So I will just delete these connections. Okay, and I'm going to make the circuit again, or let's say, let us undo all that. Yeah, so this we have made a 2:1 mux. Now let us create a new circuit, that is mux 4:1. All right, so here I'm going to take this mux and now I'm going to increase the bit width, that is I'm going to increase the bit width to 2. So now what will happen, since I have increased the bit width, that means the control signals is now going to take two the control signal is now going to take two size. 2 bits. All right. Or now to make it 4:1 mux, what we need to do is we need to change this option. I'm sorry, not the bit width option, this option, that is control signal size. Okay. So basically now you can see it has now become a 4:1 mux. So now we are going to specify the input. So we will be increasing the bit width in the option in the input in this control signal. I will just show you in a moment. First, let us put the ABCD inputs. Okay, so this is the third one and this is the fourth one. All right. So now here in 4:2 mux, you remember in 2:1 mux there was only one select line, but in 4:2 mux there are two select lines. All right. So now here you can see only one select line, right? You see now there is it is showing error, and if you look closely there is bit width error, that is 1 and 2, because this compiler knows that in order for 4:2 mux to work, this should be of 2, the bit width should be 2, or there should be 2 control signals. So here we are going to increase the bit width, that is 2. So now you can see the error is gone, and here I am going to put the output. So this is the output. Okay, so let us talk about the working. First of all, I will put the annotations. Right, so this is A, B, C and D. Okay, C. Yeah, I hope it is clear. A, B, C, D, and here I am going to write S0 and S1. Okay, and this one, this is our output. So now we are going to have a look at the truth table. Okay, so there is S0, S1 and output. All right, so the combinations are 0, 0, 1, 1. 0, 1, 0, 1. All right, so now when S0 and S1 are both 0, so you can see when S0 and S1 are both 0, the output is A. You can see it in the diagram, the output is A, that is A is 1, A is traveling to the output. Similarly, when S0 is 0 and S1 is 1, the output is B. When S0 is 1 and S1 is 0, output is C, and when both are 1, the output is G. So you can see when both are 0, the output is A, and now let's make A 0. You can see the output changes to 0. No matter I change B, C and D, there is no change in the output. So now let's make B 1, all the others are 0, and we are going to change S1. So now we can see when S0 is 0 and S1 is 1, the output will be the value at B. So you can see the moment I make S1 1 and S0 0, 1 travels to the output. Similarly, when I make them 1 0 and now I'm going to make C1, you can see the output travels, C travels at the output. Similarly, when I make both 1 1, that is G, and I make D1, D travels to the output. When I make D0, the output becomes 0. No matter I change other inputs, there is no effect on the output, because select lines, these are 1 1. So this is how a 4:1 mux works. All right. So now similarly, let us move towards all the other circuits. Okay. Let us move towards the decoder first. So now here we are going to make a decoder. Okay, so this is a decoder, and I'm going to just copy and paste, just click and drop it here. So now there is the input. Okay, now we need the outputs, that is one is there. and the other one is here. All right. So basically it is a 1:2 decoder, and generally in digital when we talk about decoders, we start from 2:4 decoder and then we move towards 3:8 and everything. So from this I'm going to make you understand the logic. Okay, so or let's move to 2:4 decoder. Okay, so just click on this decoder and here. So now I have increased the bit width, that is 2, so it becomes 2:4 decoder. So I need to increase the control bit width of this input as well. So you can see there is no error now. And now third output, and finally the fourth output. All right. So now this is our 2:4 decoder. Okay, so let me just show you the truth table of a decoder. All right, so I'm going to take this annotation. Okay, so let's say this is the input I0 and I1. All right, these are the two inputs, that is I0 and I1, and these are our outputs, that is Y0, Y1, Y2 and Y3. All right, so these are our outputs. So now let's see how a truth table of decoder works. So in a decoder we have this truth table, that is I0, I1. Okay, don't care or 0. Okay, similarly, okay, let's just put 0 here instead of don't care. Similarly, when one input is 0 and other input is 1, the Y0 is 0 and Y1 is 1, Y2 is 0, Y3 is 0. Again, for 1 0, it is 0, 0, 1, 0, and for 1 1, the Y3 gets the 1 value. All right. So here in a decoder, this is the output. Okay, so this is the truth table of a decoder. Okay, you can see the truth table from here. This one is a bit badly oriented. Okay, so here you can see when both the inputs are 0, y0 is 1 and all the other are 0. Similarly, when I1 is 1, y1 is 1 and y0, y2, y3 is 0. When both are 1, y3 is 1, and when I0 is 1 and I1 is 0, y2 is 1. So this is how a decoder works. Similarly, you can make a 3:8 decoder. All right. So you can increase the bit width and you can make a decoder that is 3:8 decoder. All right. So these are the decoders and plexers. Similarly, you can make a demultiplexer, you can make a bit selector, you can make a priority encoder. Okay, so these things you can just experiment and you can make various circuits using these things. All right. So things. All right. So now one more thing we are going to make is we are going to make the circuit of half adder. All right, and then we are going to make a circuit of full adder. So here I am going to create a project that is half adder, and now here I am going to make the circuit of a half adder, and then I am going to use that half adder to create a full adder. All right, so here to make a half adder, we all know that first what we need is an XOR gate, and then we need is an AND gate. Okay, that is for sum and carry. So here in the input, I am going to place this input, that is input A, and this one is input B, and now this is connected to A and this is connected to B. All right, so now this output, this is for sum and the other output is for carry. All right, so now the other output is for carry. Yeah. So now we can see when both the inputs are 0, 0, sum is 0, carry is 0. When one of the input is 1, sum is 1, carry is 0. When both are 1, sum is 0, carry is 1. And again, when one of the input is 1, the sum is 1, carry is 0. Okay, I will just label it as well. So this is A, this is B, okay, this is sum, and this one is carry. All right. So here I will write the truth table as well. So A, B, sum, carry. All right, 0, 0, 1, 1, 0, 1, 0, 1. All right. So when both the inputs are 0, sum is 0 and carry is 0. When one of the input is 1, sum is 1, carry is 0. Okay, when again the same case, sum is 1, carry is 0. And finally, when both the inputs are 1, sum is 0, carry is 1. All right. So this is how our circuit is working. So this we have created a half adder. All right. So now what we need to do is we need to create a full adder. So first of all, we are going to save our project online. Okay. So I am going to click on update project. So you can see our project is successfully created. Our project is successfully saved. Okay. And now here you can see I have put the access type as public. So now all of the people who are here in this CircuitVerse can search this project and can use this circuits directly as well. And for your reference, I'm going to share the link with you as well inside the course. Okay, so first of all, I'm going to launch the simulator, or also you can just search my profile on the CircuitVerse and by the name of author or name of project, and you can see the working of the circuits. All right, so now I will launch the simulator. So you can see all my designs are here. Next, I am going to create a new circuit, that is full adder. Okay, so now to create a full adder, what I am going to do is I am going to create two half adders. Okay, so what you need to do is you need to add half adder as a sub circuit. So now what we need to do is we need to go to this circuit, and there is this option, that is insert sub circuit. All right, so there is insert sub circuit, and you can see all the circuits that you have made, that is OR, AND, MUX, 4:1 MUX, decoder, half adder. So I'm going to click on half adder and I'm going to insert sub circuit. So here this is the half adder. Similarly, I'm going to insert another sub circuit, that is another half adder. So here this is the second half adder. All right, so now what is this is the A input, this is B input, this is sum, and this is carry. Similarly, this is A, this is B, and this is sum, and this is carry. All right, so now in a half adder, what we need to do is, first of all, this is the input A, this is B. So I will just create the circuit, that is this is A and this is B as it is, and similarly the sum of the A, this will be going into the input here. All right, so this is for the one of the inputs of the XOR gates. And now what we need to do is, since this is a full adder, this will be having the three inputs. So this will be having the three inputs. So this one is the third input. Okay, that is A, B, and C. And okay, just a second. Yeah, So this is the third input, that is A, B and C, and now this thing, that is this carry, is going to be ORed with this carry. All right, so here, and now I am going to use this OR gate. So there, this is the OR gate, so that we can get the final carry. So this is the final sum and this is the final carry. So here, this is the output, that is sum, and this is the output, that is carry. All right, so I am going to put the labels and then we are going to check it using the truth table. All right, this is A, B, and this one is C. Okay, this one is sum, and let's say it is C out. Okay, so now here I am going to write the truth table, that is A, B, C, sum and C out. All right, so there are 3 inputs, so this will be of 8 bits. Okay, so let me write the inputs. When all the inputs are 0, the sum is 0, okay, and C out is 0. All right, similarly, when all the inputs, when 2 inputs are 0, okay, and the other input is 1, so 0, 0, 0 and 0, 1, 1, so the sum is 1 and the C out is 0. Similarly, in this case, again 0, 1, 1 and 1, 0, 0, so sum is 1 and C out is 0. And in this case 0, 1, 1, 1, 1, sum is 0, C out is 1. Now here 1, 0, 1 and again 1, 0, 1, so the sum is 1 and C out is 0. Now in this case 1, 0, 1 and 1, 1, 0, so the sum is 0 and C out is 1. Here 1, 1, 0 and 0, 0, 0, so sum is 0 and C out is 1. Here 1, 1 is 0, okay, and 0, 1 is 1, so sum is 1 and C out is again 1. So now let us verify using the truth table. So you can see the last case, that is 1, 1, 1 and the S and C out both are 1. So let's move towards the first case, that is all are 0. So you can see the S and C out both are 0. Now when C is 1, you can see the S is 1, C out is 0. When B is 1, you can see S is 1, C out is 0. Let's say when B and A both are 1, S is 0 and C out is 1. So when A and B both are 1, S 0, C out is 1. So this is how you can see, you can verify all the combinations of a full adder. So this is how you can create a full adder using the sub circuits from 2 half adders. All right, so this is how you can create some basic circuit diagrams using half adders, using full adders, and all the decoders, multiplexer, basic logic gates. So similarly, you can create a subtractor as well. All right, you can create a full subtractor, and then you can move towards the sequential circuits, that is flip-flops and latches. Okay, and then you can create some more complex circuits like arithmetic logical unit and all the other circuits. So in this part of the course, I'm going to end it here only, because this is a basic introductory course. So that can help you to get started, and so that when you are learning, when you are studying digital, okay, when you are studying VLSI or when you are studying digital, you can analyze the circuits, okay, and you have seen all the options, so you can explore this tool as much as you want, and you can see, you can understand, and you can visually experience the working of all the logic circuits that you are studying. All right, you can see the output, you can see the result, and the best thing is this tool is very simple and easy to use. Okay, so like there are, for proper VLSI designing, there are complex tools, that is Tanner, Cadence, etc. But this tool is for the basic for the purpose of understanding, so that you can see the flow of how a circuit is working. All right. So this is all for this course. I hope you are able to understand and visualize the circuits. Now the circuits which seem so difficult can be visualized easily. And once you do by your own, it will become a lot easier. All right. So this is how you can create the circuits. And this is all for this course. Thank you guys for purchasing this course. All right. I hope you have learned something new. So thank you everyone.